Good afternoon, everyone. On behalf of all of us at the National Glass Association, thank you for making time in your day to join us for this month's installment of Thirsty Thursday. Before we begin, I do want to call attention to a couple of upcoming events. The November Thirsty Thursday will take place on the 19th at 1 p.m. Eastern. Restoring Glass Surface Blemishes will be presented by Mark Schmidt of West Cheney Elsner and Stephen Morse of Michigan Tech University. This will be a 45-minute presentation and available as this presentation has been through glassbuild.com as part of GlassBuild Connect. Speaking of GlassBuild Connect, we are pleased to announce that it will continue through December 2020, providing registered attendees on-demand access to more than 70 educational presentations and products and services from 300 or more exhibiting companies at GlassBuild. It is free to access, though registration and site login is required. Information and registration is available at glassbuild.com, and the next GlassBuild America is planned for September 13th to 15th, 2021 at the Georgia World Congress Center in Atlanta. While we're sorry we won't be meeting in person in January as previously planned for the next NGA Glass Conference, we are excited for the condensed program we'll be offering online on February 9th. It will be a great taste of activities that highlight our typical winter NGA Glass Conference. Registration will open in about a month, and we sincerely hope you'll go ahead and put a placeholder on your calendar today for this activity. I'm now pleased to introduce our speaker, Sophie Pennetier. Sophie holds over 12 years of experience in the design of complex structures and facades. She joined Enclos in 2018, where she had led various projects, specialty facades, scope sales, and design assist efforts, engaged in prototyping, modular curtain wall systems, and various research topics such as ultra-thin glass and acoustical analysis. Prior to joining Enclos, Sophie worked on international projects as a senior structural engineer with Arup in New York, where she contributed to the coordination of large design teams, complex geometry, and big data management. In 2010, she engaged in the Industry Academia Partnership research project IAPP ARC, for which she developed cold bent glass numerical analysis. Sophie authored several research papers on structural glass and is actively involved in the development of U.S. structural glass codes with ASTM, the Journal of Architectural Engineering, and the Facade Tectonics Institute, where she serves as a special advisory council and on the 2020 World Congress Organizing Committee. Sophie, welcome.
Thanks, Sarah. Can you hear me?
Yes, sounds good. Thanks.
Okay, let's get started. I'm going to stop my video and I'm going to resume it for the Q&A. So, thanks, guys. Thanks for joining today. Here's a quick overview of what we're hoping to accomplish for this 30 minutes session, 20-ish presentation followed by Q&A. So I'll give a general overview of glass forming techniques, discuss cold, warm, hot bend glass techniques, provide a bit of insight into how these relates to sizes and thicknesses that can be achieved, and show you a bit of advanced research that's happening right now. As Sarah pointed out, I'm working at Enclos, which I joined 2.5 years ago. So my background is in structural engineering. However, my involvement at Enclos has remained mostly in sales. You can see on the screen like multiple Enclos curved glass facade precedents. There's tons of them. I only touched one of them super briefly, which is on the top right corner, this gatehouse tucked behind the Chase Center arena. And I mostly help on geometry coordination. So I don't claim any expertise in any of those projects. I'm happy to talk about them and share any insights. But I can also point you to my talented colleagues that I worked on it. So I don't claim neither to be a manufacturer of curved glass. I'm joining Enclos, which is designing, manufacturing, and installing curtain wall. So I only claim my passion for structural glass and all of its versatile uses. So when my So the glass we use in architecture is celluloid glass. It's a very strong material and a quite elastic material. So in terms of elasticity, it has the same Young modulus as aluminum, which means if you want to bend a sheet of aluminum or sheet of glass at same thickness, it's going to have the same flexibility. However, it's not ductile like aluminum is. It's produced in, for architecture, it's produced into these three types of product: annealed, heat strengthened, and fully tempered. As you guys know, annealed is what we see mostly around us in window glass, and fully tempered is a very fast, cool product, which confers this surface compression to the glass, which makes it much stronger, but also what results in breaking into like those small pieces, whereas the annealed glass itself typically breaks in larger shards, which can be a good breakage behavior to leverage if desired. So I'm always asked, what's the strength of glass? Well, here's this really beautiful table put together by our friends at EOC and dispatched into this ANC SEAG glass guide. And the answer is quite complex. The strength of glass depends, first of all, depends on where you are in the glass, on the edge, on the center. It depends on the edge condition of the glass, how polished the edges are, not only of the edge of the panels, but any holes you may have or any funky cuts. It depends on the duration of the load. So what it means is basically the glass is this brittle material that has cracks, and so as the longer you load it, the longer the stress you have on those cracks, and they slowly want to open, right? And so a longer load is gonna have a greater capacity to propagate those cracks and break. So it also depends on where it is in the building. Is it overhead? Is it like this general infill? So that results into an acceptable probability of breakage. This is where you have those left-hand side tables and right-hand side tables, and different acceptable stresses. So yeah, the strength of glass is a question that results in a very long answer. And lastly, it also depends on, as I was saying, those three types of glass, which are annealed, heat strengthened, and fully tempered. Today, I'll talk about, here's the map of what I will be talking about today: hot, warm, and cold bend glass. I like one pager, that's the way I think. So on the hot side, which consists in actually melting the glass or softening the glass into shape, you got a slump glass, which are called by certain manufacturers curved anneal, the gravity curved, that's made into a kiln. And we'll get to, let me go over all of this. So you get some glass. Curved tempered glass are done on those tempering lines that are shown here on the screen, and composed of rollers and rocking the glass. It's a bit of a lesser static behavior or fabrication process, sorry, but it results in tempered glass. And as you saw earlier, you can have leverage a lot of strength from that type of glass. Warming glass is called such because it leverages the interlayer to help forming the lights of glass. So it's called warm because of the temperature of the oven when you laminate those sandwich panels. I'll get to it in further details. It's also called laminate bending, two-step bending, with all sorts of new things. It's actually has a lot of names, but I prefer hot, warm, and cold. This is pretty straightforward, and that's what I call it. And then cold bend glass, which you can form on the shop or on a site, and that consists in elastically deforming the glass. As I said earlier, it's quite flexible material. They all result in different types of visual quality, different strength. So let's dive into these ones into further details. So hot band glass. Starting with slump glass, basically the process consists in placing the flat float sheets of glass onto a mold that's typically made of steel, protected by some fiber meshes, so that you can allow the glass to kind of slide onto the surface as it's slowly softening, and then putting it into another into a kiln, sorry. So typically the limitations are going to be the size of the kiln itself, but also the thicknesses also of the glass. When it comes to radius, this is the technique that allows for the tightest radius available for architectural glass. And that also depends on the thickness of the glass. So the thinner glass, you can go down to, and again, the numbers I'm giving is my own personal review of what suppliers can supply us on the market, and you might want to contact them to see if those work for your project. But the minimum radius that we can go at are, for instance, for 4 millimeter glass, you can go down to 100 mil, and for 8 millimeters or greater, you can go to 300 or 350 millimeter radius. And so that is dependent on the size of the full glass, the width, and its thickness. One thing I forgot. The type of geometry you can achieve with this technology is probably the most versatile of all the forming techniques that we have at hand. You can have doubly curved panels quite easily because you're basically, you're baking the glass basically, and so you can have those S-shaped, funky shapes, even some only local curving within a panel. So it's very versatile. Whereas the next couple of techniques I'm going to describe are a bit more restricted because of the technology itself. So this there's many glass bending companies that have those type of equipment, and they vary in size, obviously. But that line allows you to shape the glass with the help of those basically those rollers. So the glass is heated up and then put into this area that deforms and pushes the glass into place, and it's rocked into place so that it can be this is when you cool it down, this is what's called quenching. You basically through all of those little nozzles locally pull some air into the glass to giving it its very, very fast cooling rate. Again, we're going from the order of magnitude, don't quote the numbers, but the order of magnitude of 1,000 Fahrenheit down to room temperature very, very quickly. And so as a result, that quick cooling that's provided by the quenching of all of these nozzles is providing that temper to the glass. And the reason why you need to quench it is you want to make sure you don't have a static glass under a local nozzle, because what happens if you don't rock the glass around, you might have some local stress concentration, which you don't want for the structural behavior performance of your panel, but also visual deformation due to those localized quenching marks. So you need to rock it, and so as a result of that rocking, that technology limits the geometry that you can achieve. You can imagine that if I had a little S shape or something quite complex in that under those rolls, I wouldn't be able to just move it in place. So that's how that drives the geometry that you can access with this. So that is also the technology that gives you the greatest panels, the greatest panels available. So if I go back to my first slide, you can get to panels up to beyond 6 meters, and for certain applications even more. Again, that also depends on other factors related to if you want to heat soak your system, if you want to have some fritz and interlayer and so forth. But in general, that's the technology that can give you the longest hot bend panels. Warm bend glass consists in piling up sheets of glass and interlayer. You just stack them on top of each other, throw them into a vacuum bag and clamp it into some sort of jig that then you roll into your autoclave and laminate as such. So when you've pushed the glass in place, you've elastically deformed it, and this is how the glass is shaped. But when the laminate itself gets out of your autoclave, that's the interlayer that prevents the glass from coming flat again. And so there's a load transfer from each glass transfers loads to the interlayer to the next glass over, etc. And so that loss or long-term behavior, I guess, of the performance of the interlayer at interface is critical with that technology. That has been used for the Strasbourg rail station in France. These are the panels right after fabrication, and these are the panels during installation. This is a system that has an internal spring back forces, and so you want to be able to capture them and to also understand how long the interlayer is going to be maintaining these components in shape. And I did some research about it. I'll describe down the line. Looks like I'm still in the general presentation and not yet in the weeds quite there. These are these beautiful hot bend panels slide that was flying around, not where it's supposed to be. So let's go to wrap up the overall overview of the techniques, finish with cold bend glass. So again, glass is this fantastic elastical material if you know how to design it, but it's quite often not the limiting factor. It's quite often going to be the components of IGUs or interlayers that might actually limit the performance. So that's why I differentiate these into two columns here, because again, the glass is not always the limiting factor. One really cool application of cold bend glass laminates here. My Enclos is the Cobo Expansion Center in Detroit, where the glass was slightly curved. So you got this, the glass came planar and were deformed about 1 inch inward by the means of tensioning those bolts that were at the spiders. Let me show you. That's the project, and the canopy is right there. This is the full canopy, and that's the detail I wanted to point out to you. So this is the spider here that by in and out brings the glass in. This was a 1010 laminate with SGP, and that was basically pulled inwards by the equivalent of the thickness of one panel. But the second part of it is IGU. So there's some really cool work out there that has been already built, such as the ISC headquarters in New York City, or the Avignon railway station in France. And they leverage the capacity of the subcomponents of an IGU to actually maintain the state of this shape. And there's this really sweet research by Sika, and also all that good work that has been presented at GPD in the past couple of years that shows basically the limitation of cold bending and IGU. And quite typically, I invite you to go read that paper, but if you have to only remember the limitation in in geometry here is no longer the glass and what we saw in terms of shape and capacity of the glass manufacturers, but this is the capacity of the secondary seal here, or the any structural basic joint to maintain long-term loading. And these materials are not really good at maintaining like long-term shear out there, so they just need to be sized adequately. And so that could be a limitation for the freeform facade that you might want to panel with glass. So before I moved to the US, I was in France at RFR. I was seconded to the University of Technology in Vienna. We had a partnership, so throughout the last 2 years of when I was there, I was in and out of some specific task for this research, where we looked at the paneling of freeform surfaces with single curve panels. That partnership was with not only the University of Vienna, but also Evolut, who are doing this plugin for Rhino. And looking into, my work was looking into the specific to the cold bend glass and warm bend glass. So I've developed internal tool to look at the loss of shear bonds in the long-term loading of laminates. So basically, in short term, a laminate behaves like a full, close to full, if not a quite good composite. And in long term, there's a loss of shear at interlayers, and this is what I studied. So how does all that we know there affects glass design and paneling in the long term? So I retrieved some data on long-term shear behavior of interlayers. So basically, a very long creep and loss of mechanical property. And that same project followed my numerical analysis with some testing that was done at ITKE in Stuttgart, and looking at how these curved laminates reacted throughout time. So you can go out and find those papers. I'd be happy to share them with you if you just email me. We looked at multiple type of laminates using PVB, SGP with 2 or 3 plies. And so as you see in this graphic, the loss of stiffness of the interlayer has a reciprocate into a flattening of those compounds. So again, these were fabricated in warm bend technique. This is what people call laminated laminate bending. So basically, we were just looking at the interlayers on it to keep the shape. And so the interlayer itself lost its capacity, in its immediate capacity, if you compare to like a very short loading of less than a second compared to like a couple months, you can go from a factor to 1 to 3%. So typically we saw that PVB's interlayers became super flat again after basically just a couple minutes, but that was something that could be leveraged if you had to just place as an intermediate installation sequence. That could be quite interesting to leverage. But in the long term, the SGP interlayers and SGP laminates behave much better. So I invite you to go and look into more details and ask if you have any questions. And that same work was exhibited at the GlassTech in 2014 with at the booth of the ITKE, who did the testing that was financed by the project research I was part of. And you could go, for the lucky ones that were out there, see live how much stress you were imposing on the glass, and how much stress was left into the system. Another really cool body of research, still by the Vienna University of Technology, with whom I was working, is this paper that just published at SIGGRAPH this year, with the latest advance of the tool I worked on, or actually contributed. humbly and minimally. This tool enables a live modification of the geometry of the freeform surface you're trying to panelize, and a study on how it can be achieved with various specific constraints. That the ultimate goal that I was helping on to try to bring the mechanical material constraints of the material right there. They're also looking at those geometrical constraints. Are you looking at single curvature, double curvature? If it's double curvature, as I said earlier, you can achieve with warm band glass or some very limited warpage of the cold band glass, etc. So that's quite a cool tool, and you should reach out to them if you have any questions. They're also looking not only at the geometry of the panels themselves, but also the kinks at the interface between panels of different curvature. So that can be quite interesting as well. And that was leveraged on the True project. That was actually part of the research program I was on. So it's still on the same page. You can find some of my research, but also that specific publication on the Eiffel Tower booth that leveraged multiple types of geometry, curvature, and was meant to use multiple techniques, but didn't go that route. But you can see how that tool was used for the True project. And lastly, we're going there are multiple other types of glass products that are not all soda-lime glass, but that can be leveraged into not only being used as such, but also aware of rethinking the way we curve glass. And that's what's happening here. This is the Gorilla Glass with kerning, and this is being used for interior applications, not so much yet in envelope, but hopefully soon, or for this dashboard they're looking at typically with Renault and flexible electronics. And I have been working with this material on a little sculpture, and you can go into this the GPT presentation to hear more about it, but looking at how when we leverage the flexibility of the material combined with a geometry that's corrugated and that provides as an assembly provides some stiffness, we can achieve geometries that are quite atypical for glass. So this is the final product, and this is the product after a really hot and tough summer, after a bit of breakage. But I think that scale is interesting for prototyping, for leverage, like different thinking about curved glass. But I think it can be also used in lightweight systems such as skylights, or being integrated in all sorts of other glass products or compounds such as IGUs, etc. So with this, I'm closing that presentation on glass curving. I hope I blasted enough ideas to open the conversation, but also to show you that it is not a very simple answer. What's the size of glass? What's the type? What's the strength? Because there's a lot of parameters to be taken into account. But what I hope I've conveyed is that there's lots of research happening that is broadening the scope of what you, the curving technology that's out there, and also the potential for not only expanding today's manufacturing capacity, but also rethink how to combine different type of technology and incorporating it very early in a design so that it can be leveraged only early and bring those visions to life. So with that, I'm gonna finish our presentation. Thank you for our attendance, and also I look forward to your questions.
Excellent, thank you, Sophie. We have a few that are coming in the Q&A, and first one, can you just comment on thermal stress on bent glass?
Sure thing. So there's multiple thermal stresses, and maybe that whomever has asked the question can chime in. But in terms of the residual stresses, or in terms of external loading on glass, that's something I would be quite interested to hear what the background behind this question. But this is a very broad question, actually. So if we're talking about the cooling, differential cooling stresses that are happening at a differential rate into the glass, that's that can indeed induce a lot of stresses. In terms of thermal loading in long term of a monolithic lights of glass, I mean, this is something that can be quite easily modeled in FE. So you know the orientation of your glass, the source of thermal loading. But the most important point is the detailing and making sure you allow your glass to be able to expand. And if you don't do so, or if you don't have the right capacity of the glass to sustain those stresses, this is where you have a risk of breakage. So typically, if you know that you have a pretty high thermal load, for instance, if you're on a south facade and you have like a black freight and something that's quite opaque and that keeps the induces a pretty high thermal load on the glass, you want to make sure you have enough residual compression capacity. So you want to go into probably like heat strengthened glass, fully tempered glass that have the capacity to sustain the thermal stress. But again, it goes two ways. You make sure that you first of all detail it accordingly to let the glass expand if it needs to.
Okay, great. Thank you, Sophie. If we can move on to another question. Let's see, for warm glass, warm bent, the lamination layer holds the glass shape, and how is the stress on the glass? Can only laminated glass be used this way, or can heat strengthened or fully tempered or annealed be used?
So first of all, you can laminate anything, literally anything, any material or type or pretty much anything. So laminated glass is not a fourth category. So I hope it's understood. So then when you start laminating those type of product, you want to go into understanding what's their own different capacity, and you want to also see how much load you transfer between one light and another when you calculate those things. So yeah, you can use warm bent glass with any type of glass. Basically, you just want to make sure you don't reach the capacity of any of the substrate or any of the plies you use.
Okay, great. Another one, what is your preferred, what software do you often use for bent glass analysis?
I personally, I'm used to work with strand 7. In Europe, it's called Strauss. But you can use pretty much, I mean, it's a very good software for its capacity for actually the meshing capacity is the part I love the most. And it's quite better than other packages, but you can use SAP 2000 or GSA as long as you got the right. You can also use ANSYS. Actually, some of the work we used for that research, we used ANSYS and Codaster. So it's quite versatile. What you just want to make sure is you got the right meshing tools, if not embedded in the software packages. And you also need to make sure you have nonlinear materials and capacity, because you want to be able to vary properties of material if you have to, and capture the history of loading as well. So being able to do a stage analysis.
Okay, great. Another question, this one regarding IGUs. Can you comment on, pressure due to climate loads and how that impacts IGUs stiffness?
Yeah, so climatic load, I'd be curious to see if the person is thinking about like wind loads or thermal loads or isocharacteric pressures. There's tons of good stuff out there, and there's a lot of really good papers. But
this is in regard to internal pressure.
Okay, isocharacteric pressures. Yeah, that's a very good question, and there's some other good work I can point you guys to. But in a nutshell, you got this gas volume in there that's when it's heated up, you might have those isocharacteric pressures, and yeah, that's an extra load, and you need to add up onto your long-term shear of the subcomponents that are making the IGUs, and that's something you can totally model in stress 7 actually. So I'm not too sure actually what's the problem in there, but yeah, definitely you need to integrate it into your analysis. That's for sure.
Okay, great. If you have time for a couple more questions, can you comment on your experience with Gorilla Glass and methods for curving that?
Sure thing. I actually myself didn't work with Gorilla. I worked with Willow Glass. That's a much thinner product. Gorilla is gonna be in the range of 0.7 millimeter, so 700 micron. And the Willow Glass I've been working with my sculpture is, you can have it in multiple thicknesses, but you have 100 and 200 micron per predominantly. And these come in long spools of 4 feet wide, so 1.2 meters, and roughly 300 meters. So that's virtually infinite. And so I invite you to go read some of the papers I put out there, but you can cut it as such. It's not so the the Gorilla itself is tempered. So if you try to cut it, and after it has been fabricated, after it has been chemically tempered, you might run into some problems. And that's not the case for the Willow Glass. It's ultra thin glass. So you can basically just scribe and break it the same way you break your bathroom tile. So that's pretty much the way you work with annealed glass. You because it doesn't have its residual stresses. The Gorilla Glass can be machined. Yeah, you just need to just need to do that before chemical temper. I didn't mention chemical tempering of the glass out there. It's an extra processing you can have on glass that provides the capacity of or / beyond a fully tempered glass, but a breakage pattern that's in greater shards so that you don't have that type of problems. It has its own limitation on how much the bath can take. It's up to you if you decide to use the chemical tempering processes. That is a staging, as I said, that is require all of your machinings and holes to be done before the chemical temper.
Okay, great. Maybe one more kind of technical question and then a couple of future trend-based ones. Do you monitor the Gare de Strasbourg, and how well does it age?
That's a really good question. I do not know. One thing that we all know is happening is a load transfer between the warm band glass and the supporting structure. But this has been designed to be to have a full load of transfer to the structure. So basically, whether if it was curved in the shop or on site, the let me rephrase that. The capacity itself is capable of sustaining all of those stresses. So basically, we're talking about polymers there. And when you look again at my little graph, there is ultimately in a very, very long time away, if you just shrink this logarithmic scale, you're going to go back to flat again. The question is, when does that happen? Does it happen before installation or after installation? But you can't assume that the interior is going to withhold, just the interior is going to withhold that stress forever. I do not think it's wise to design like that. I've not seen it myself, but I think we need to have resilient structures that can take all of that load in case the creep of the interiors just results into like the full drop of its mechanical properties in terms of long-term shear. So no, I look forward to hear if there's anything coming up. I haven't heard anything coming up on Strasbourg. Something to be noted though is that they're not IGUs. They're just two-ply laminates actually. So there's less component to be wary of. There's no primary, secondary seal things that are happening. So for that specific type of curving, I think it's a wise design strategy.
Okay, great. Looking ahead, what does the future of bent glass hold, considering we're using bigger and bigger panels? Which method, cold versus warm versus hot, is ideal once you move to jumbo glass?
Once you move to general glass?
Sorry, jumbo or oversized.
Oh, jumbo.
Mm-hmm.
I think, I mean, it really depends on the geometry, the intent of the geometry. It's a hard question, but if you have a really tight radii, you are down to tight or compound radii, you're down to a fabrication technology that's more manual, and as it should be for slam glass. So where's the future? I hope I would see more fabrication informed design as opposed to some sort of passive reaction of the market. So the future for me is going to be, hopefully we see geometry that responds to an adequate, how to put it appropriately, the adequate use of manual lever for tight radius and automatization for different other type of geometries. I can see it's everywhere, and I can only tell you that the future has more and more curved glass. It's better understood, it's better tested, and also it has its own advantages, like the aerodynamism of this building right on the screen, the stiffness provided by curved glass, all sorts of good things that have not just a visual impact, but also makes sense from a structural standpoint. It also is also a question that we can bounce to our friends that are looking at ventilation of those spaces, it has its own advantages. So no, I can see more and more curved glass coming up for holistic design reasons.
That's excellent to hear. Thank you, Sophie. I think we have a few more questions that I think we'll need to reserve for our offline response, but we'll make sure to download and track those so that we can follow up with you. If you enjoyed this topic, which it seems like you did, and you're involved in bent glass fabrication and design and are an NGA member, please contact Amber Johnson. We'll put her email in the chat, ajohnson@glass.org. To be kept informed of a new task group that may be formed within NGA's technical and advocacy department so we can continue diving deeper into this. We again hope to see you on November 19th for our next Thirsty Thursday, hosted through glassbuild.com. Sophie, thank you again for sharing your time and expertise with us this afternoon. It was an excellent presentation.
Pleasure in mine. I look forward to continuing the dialogue.
Excellent. Thank you. Have a good afternoon, all.
Bye, everyone.